All right, everyone, welcome to another episode of the TWiML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Doina Precup. Doina is a research team lead at DeepMind Montreal and a professor at McGill University. Before we get going, be sure to take a moment to leave us a 5-star rating and review wherever you're listening to today's podcast. Doina, this conversation has been a while in the making, and I'm super excited to have you on the show and looking forward to digging into your research into reinforcement learning. Welcome.
Thank you very much. I'm really excited to be on your show and big fan of your podcast. So looking forward to our conversation.
Awesome. Same here. Let's get started, as you know, we always do, by having you share a little bit about your background and introduce yourself to our audience.
Yeah, so I split my time between DeepMind in the Montreal team as well as McGill University, where I've been a professor since 2000. Before that, I did my PhD at University of Massachusetts Amherst, working on reinforcement learning. I was actually lucky enough to take the first version of the reinforcement learning course taught by Andy Barto and Rich Sutton out of their textbook back in 1995. And it got me hooked to the field, and I've been working on it ever since.
Fantastic. And what prompted your interest in RL?
I really found it a good way to think about artificial general intelligence. So agents that can learn how to do many different things in an open-ended environment. And it's really because we have, on one hand, rewards that give us a way to express the task that the agent should do. And on the other hand, we really have learning from interaction rather than, let's say, learning from being told what to do or not really having a clear goal. And so it seemed to me to be the right sort of balance between having some interesting signal in the reward, but also having this ability to interact and explore and really learn freely in the environment.
Right. RL is increasingly a broad field. So let's dig a little bit into your research and have you share a bit about what you're most excited about.
So one of the things that I've worked on for a long time, and I'm always excited to think about it, is hierarchical reinforcement learning. This is really about learning abstract representations, especially abstraction over time, because oftentimes in reinforcement learning, the problem is phrased at a very small time scale, very fine-grained time scale, sort of on the order of, let's say, muscle twitches. But really, to solve complicated problems, you need to think in terms of longer timescales and variable timescales. So, for example, if you're cooking a meal, you're not thinking about all the muscle twitches involved in stirring or putting a pot on the stove. You're thinking in terms of larger steps. What ingredients do I need? Do I need to go to the store to get these ingredients? And so we reason at many levels of abstraction, both in terms of the timescale of our actions, as well as in terms of the states and features that we use. And I would really like reinforcement learning agents to be able to do the same, to really leverage abstraction and learn these abstractions from their interaction stream. So I've been doing a lot of work in this respect in terms of, for example, learning a framework for temporal abstractions called options, learning models that look at different time scales, understanding how to use these models in planning algorithms, and also understanding when agents can use what actions, what we call affordances. And so this is a long history and a long series of papers that is associated with it. But one of the important open questions that I still struggle with and think about is, how do agents decide which abstractions to learn about? For us, maybe it's easy. We think about objects, for example, and that somehow comes naturally. But for reinforcement learning agents, this is still something that I would like them to acquire automatically.
Awesome. And we'll return back to hierarchical RL. You also spent a lot of time working on reward specification for RL agents. Can you tell us a little bit about that work?
Yeah, so rewards are actually really important because they determine what the agent is really learning about and thinking about. And David Silver, Rich Sutton, Satinder Singh, and I put out a paper in 2020, which received quite a bit of attention, both positive and negative, I think, called "The Reward is Enough." It really talks about this hypothesis that a reward signal, in fact, a simple reward signal in a complex environment could really lead an agent to develop all the interesting attributes of intelligence that we might sort of intuitively think about. So, for example, in this paper, we discussed squirrels. Squirrels have perhaps a simple reward function. They like to eat nuts because that helps them to survive. But in that process, they actually develop a lot of interesting abilities, like the ability to remember where they've put nuts before, and the ability to predict the time of year when these are going to be available, and the ability to deal with other squirrels and maybe deceive them or make sure that they don't get to the hidden stash of their own nuts. And so that's an interesting set of abilities that involves memory and planning and modeling aspects of the world that can all be seen as developed from this maximization of reward. And so we were asking ourselves in this hypothesis whether it could also be true that general AI agents would develop these kinds of abilities also from maximizing rewards. It's a hypothesis. And so, as any hypothesis, it's interesting to think about how we might confirm or dismiss it. And so, following that, we did some technical work trying to understand how we can take sort of intuitive task specifications and translate them into rewards for reinforcement learning agents. And when is this actually possible? So, this was a paper called On the Expressivity of Markov Reward that was led by David Abel and with several fantastic collaborators at DeepMind and also at Brown University. And it received the Best Paper Award at NeruIPS last year. So that was also a very welcome surprise, actually. When we wrote the paper, we weren't sure what people would make of it. Um, but we were quite excited to see the positive reception. And really, in the paper, we aimed to make this hypothesis a bit more concrete and to try and understand from a mathematical point of view, when do Markovian rewards, which are a special class of reward functions, capture intuitive notion of tasks.
Got it. Let's maybe start with the general case of rewards. The hypothesis is that using this mechanism of reward can lead to all sorts of intelligence capabilities, behaviors. How do you characterize that in a machine learning context? How do you draw the analogy from the squirrel to machine learning?
So in the paper, we thought of essentially a framework where you might imagine somebody who has a task in mind. Let's call this Alice. And then you have a learner, call the learner Bob. And so Alice has a task specification in mind and now has to translate this into a reward signal that Bob would get. So Bob is a usual reinforcement learning agent. It inhabits a Markov decision process. This means that on every time step, Bob observes the state of the environment, can do some action, and then will receive as a response an immediate numerical reward signal, and there will be a transition to a next state. And there's some discount factor that devalues rewards that are received too far in the future. And Alice might have something more intuitive in mind. So, for example, Alice might have a preference over certain ways of behaving. So, if Bob is an agent that's in a grid world navigation task, for example, Alice might prefer that Bob gets to a designated goal location quickly, but she might also prefer that Bob doesn't step into lava and get burned. And so this imposes now a preference over the set of policies that Bob might have. The policy being the mapping from state to actions, and now we can think of the task specification in Alice's head as being this preference over the space of policies. The reward function is the usual Markovian reward, which is associated with states and actions. And we want to understand, can Alice efficiently compute a reward that captures her preferences? And so now we can think a little bit about, what kind of preferences she might have and how stringent they might be. So one kind of preference, which I described, is over policies. And we can have that be very strict, or we can relax it a little bit. We can say, Alice certainly thinks that some actions are bad, like stepping into lava is always bad, but otherwise has no strong preferences in other situations. So whether Bob takes one route or some other route doesn't really matter, so long as he doesn't get burned. So that leads us to ranges of policies, or sort of sets of policies, being acceptable or being superior to others. And we can also think in terms of trajectories. So Alice might consider trajectories that Bob might do in the environment and just prefer one trajectory over another, right? So if Bob is not trying to run into walls too much, maybe that's that's a good thing. Um, so now, if we have a set of preferences like this, the question is, can we actually always translate them into a reward function? So can Alice compute a reward function that is Markovian? And if so, what's the complexity of doing this? So the paper has two aspects to it, right? There's a negative result and there's a positive result. The negative result is in hindsight not so unexpected, but it basically says you can't always find a Markovian reward, Markovian in the state of the agent. And intuitively, in hindsight, it's not so surprising, because on one hand, there may be states that are unreachable, where Alice might have certain preferences, but they're irrelevant. And so if you have some disconnected state in some corner, and Alice has some contradictory preferences there, let's say in terms of the actions, that can impact the specification of the reward overall, but it's a case that we don't really care about. So that's sort of one mode of failure, which is perhaps not interesting.
Would it be an example like if Alice, if the maze is, nominally 20 steps to completion and Alice has a preference that you get there in 3 steps, like it just can't be done?
That's right. So this
Yeah.
kind of thing is, it's impossible, and therefore, uh, the math says yes, yes, it's impossible. There's a more interesting case, which is the case of non-Markovianness. So, for example, Alice might say, "I prefer that Bob always go in the same direction. So, if you're going up, you should always go up. If you're going down, you should always go down."
Markov decisions are IID, so you can't really enforce that.
So you can't really enforce that. If you wanted to enforce that, one possibility would be that you modify the state space, right? So that we keep track of, whether you've been going up, and then, we could do a Markovian reward in that. But in this paper, we only considered specifying with respect to the state space that's already there. We didn't consider this larger context of, trying to modify the states and specify the reward. I think it would be a very interesting avenue for future work to think about how do we go from observations to a specification that has, perhaps a new state space and a reward function that goes with it. But that went beyond the scope of the results that we had in this paper. However, one thing that we did show in the paper, which is the positive result, is that there is a procedure, which is a polynomial time procedure, that Alice can use to either return a reward function that is consistent with her preferences, if such a reward function exists, or to determine that no such reward function is possible. And the intuition actually of the algorithm is interesting. It's based on a linear programming approach. And so the basic idea is that for any policy, we can compute a stationary distribution associated with that policy, stationary distribution over the states of the controlled Markov process. And then we can impose constraints between the policies that are in Alice's acceptable set and the fringe policies. The fringe policies are identical to those that are in the acceptable set, except at one state they would take a different action. And so we can have a set of inequality constraints that basically say the acceptable policies should be better in value than these fringe policies. And with this kind of linear program, either we find a solution and the size of the linear program is polynomial in the size of the states and actions, so we can find a solution in polynomial time. Or if the linear program does not have a solution, that means that no Markovian reward function is actually consistent with the original preferences that were expressed.
Is there a notion of like sometimes a linear program is underspecified? You've got more degrees of freedom than you have constraints. Does that come up in this analysis?
That's a really interesting question. No, in our case, we want to find a solution. If any solution is okay, we don't need to find a specific solution. And so there will be, for example, potentially multiple reward functions that are all consistent with some optimal policy. Um, for example, scalings of each other, and that's perfectly fine. So long as all of them end up ensuring that the preferences are satisfied, so the good policies are better than the others, right? Or that the bad policies are inferior to the others, then all of these solutions are fine and acceptable from our point of view.
There's an implicit assumption that the policy is specifiable kind of mathematically, or not the policy, sorry, the preference, which maybe limits maybe this is referring back to what we were talking about in terms of the Markovianness of it. But it also kind of speaks to the gap between a preference that someone might have in a real world scenario and then trying to implement it using this method. And how do you get to a mathematical representation of that preference? Like, did you address that at all in the paper?
Yeah, so that's an interesting question, and we don't really talk about this in the paper, but I can give you my perspective on this.
Okay.
Um, on one hand, what you do in the real world is you have some preferences, but you may not have full preferences, right? So you might, for example, in our grid world, say, well, Bob should never step in lava. But if Bob has to go through red squares or green squares, I don't really care. Okay. But as you observe behavior, those preferences might actually change, right? You might start preferring, that Bob maybe always steps on green squares because those are soft and, Bob is like a little toddler and shouldn't hurt himself, right? So these kinds of things may come up over time. Now, our framework is very much single shot. So Alice has a set of preferences. They're there from the beginning. She computes the reward, and then Bob goes off and optimizes that reward function. I think in practice, there's much more of a give and take, right? There is much more of, maybe Alice observes the behavior that might get her to have new preferences, right? Or maybe revise existing preferences. And so I think in applications, one would have to have an interaction loop where, Alice observes, gives new reward functions, Bob continues to optimize over time. And this continues for a while in order to really get to the root of what the task is. And, one thing that I remember, for example, is when my kids were young, we used to reward them for putting away their toys. And at some point, one of them discovered this interesting strategy of always taking all the toys out of the toy chest and putting them back, and taking them out and putting them back, because it's the behavior that gets rewarded, right? So
It's the
uh,
classic boat spinning in the middle of the that game.
yeah. So basically, now this is the stage at which one would actually revise what the reward function
Right.
is
Right.
by observing the quirkiness in the behavior that is being induced. And I think naturally we do that, and our framework in this paper does not address that. There's one other aspect which is also not addressed, which is with how good is this reward function in order to get Bob to learn efficiently. So this is not something that we talked about in the paper at all. We interestingly observed that in the examples that we showcased in the paper, the inferred rewards did lead to fast learning because the reward function is the result of computing an LP, and so it's a dense reward function. It's not sparse like what people would specify in these kinds of tasks. And so it does lead as a side effect of that to pretty fast learning, but it's sort of it's not clear that that would always happen.
So the linear program serves to constrain the search space for the reward function, which yields more efficiency.
Yeah, exactly.
Yeah, I think my question, maybe I'll come at my question a little bit differently. The example you use in the paper is grid world. Yeah, maybe it's the case that any preference about actions in grid world, there's a straightforward mathematical representation of those. In lots of other, tasks, maybe there's not a straightforward mathematical representation of the preferences. Um, but I guess I'm supposing that there are Markovian tasks for which the preferences are not easily mathematically represented. That may not be the case, but um, did you look at like what tasks or environments this all of this applies to?
That's a great question. So the paper itself is more of a definitional paper. We were trying to define the problem, think about what it means to have a task in mind, and separate that from this issue of how do you then specify it as a reward. Um, there's so it does assume that you have a Markovian process, and the side effect of that is that we have states. Now, in the real world, we have features, right? We don't have states, but we have some observations. We see images, right? Those are an imperfect representation of what the state might be. And that is not a setting that we have handled in the paper, although I think it's really interesting for future work. So, Alice might have preferences, but might not have access to the state space. She might only have access to observations. And Bob also might not have access to the state space, only to observations. And this is where the framework that we have and the specifics of the LP would not carry through. I think there is a path to have a similar kind of solution in this case because, generally speaking, in reinforcement learning, LP formulations have been used as a way to think about the problem of reinforcement learning. And there are versions of these approximate linear LPs, infinite LPs, that have been proposed for other kinds of reinforcement learning problems. So my gut feeling is we could take some of that methodology maybe and apply it in the case where you don't have access to state. We do assume that Alice has preferences. And so if she doesn't, or if she doesn't know what they are, our work doesn't doesn't help with that. But I think this limitation, for example, of not having necessarily an MDP, having features, these are things that are more left for future work, but could potentially be overcome. It would also be really interesting to think about how preferences might be obtained in practice. Like what if you actually had an agent that is working in a loop with a person? The person is stating some preferences. We use this methodology to extract rewards, and then maybe again the person observes what's happening and goes back and is there a way for us to really do this in practical applications? It's not something that we have tried, but it would be fascinating to see.
And part of the problem is the one you articulated earlier is the of evolution of preferences over time, that you have to do that plus the trying to figure out how to close that loop in real time.
Exactly.
Okay, going back to the work on hierarchical reinforcement learning, is there a recent paper in that space that comes to mind, or maybe we can talk a little bit about or start from like the kind of what's the research frontier there? How far along are we in thinking about these kinds of hierarchical problems?
A lot of the work over time has gone into the question of discovery. How does an agent discover abstractions? We have a lot of good understanding about how to represent, for example, temporally extended actions, by having an initiation set where such an action can start, by having an internal policy and then a termination condition. So this is a framework called options in hierarchical reinforcement learning that I worked on for a very long time.
And what would be an example of that?
Imagine that you have a robot that's in an environment and it has a controller, and the controller says you can go forward if there's nothing in front of you. So if you're far enough from any obstacle, that's your initiation set. It's almost the entire environment except for some spaces around your obstacles. The policy is just to go forward, so that's already pre-specified, and you stop whenever you're too close to an obstacle. So that's the termination condition. And now these policies can be stochastic as well, right? So it doesn't necessarily have to be that you're always going forward. You might be going on any kind of path, right, until you get too close to an obstacle. And such controllers can be thought of not just in robotics, but more intuitively, for example, in planning, right? So if you're playing, let's say, a puzzle game like a Rubik's cube, you might have certain configurations that you want to achieve that impose sub goals, and then the ways to achieve those configurations can be thought of as these kinds of options. um, so we understand how to formulate the problem. The interesting question that is still quite open is, how do we actually find these sub goals? So for example, in a Rubik's cube, I don't know if you've ever done any of these, or if you like them, but when you learn how to do them, people will tell you, oh, you have to complete a face, right? Somebody's telling you that's your sub goal: complete the face. That's the first thing you should do. And then if you have this kind of configuration on the side, here's a little sequence that you should do, right? To- So it's told to you, and yes, once you know this, it really greatly simplifies the problem, because you don't search through all the space of possible moves. You're now executing these sequences that are useful. Um, but how do we discover this on our own, right? That's the key question, and it's one that we've thought about quite a bit as a community. It's still pretty open because it's hard. There are some interesting answers. One interesting answer that one of my PhD students at McGill, Pierre-Luc Bacon, did a few years back is called Option Critic. It's basically an algorithm that tries to use the reward from the environment and tries to find sub goals that are on the path to rewarding states. And it uses gradient based methods very similar to actor critic policy gradient methods. And so that works quite well in certain environments, but sometimes we still observe things like the agent using abstractions for some bit and then kind of collapsing them away, like getting rid of them. And it, again, in hindsight, maybe one should expect this, because if you think about how people do things, oftentimes you need these kinds of hints or sub goals at the beginning of solving a task. But if you're only solving one task and you get used to it, you don't have to think about that anymore. You automatize it away, right? So people who do the Rubik's Cube in a few seconds don't really think about the configurations anymore. Like, it's all gotten into their muscle memory. And so it's a similar situation that we observe with our agents. If they only have to solve one task, they might use options for a while to try and help them out, but then they get rid of them and they obtain some flat policy that is as close to optimal as possible. So one way to think about this is the agents only have to do one thing, and so they're overfitting to that in some sense. If they had a very rich, very large environment, complex environment with many things to do, they may need to keep these abstractions around. So if you're not always having to solve Rubik's cube, but you have to solve different kinds of puzzles, right? Let's say number puzzles, then you might have certain strategies that you learn and you do keep around about, how to manipulate numbers, for example, in these puzzles, or how to do a search. That's the kind of richness that we would need for our agents to keep these abstractions around. And so part of it, I think, is thinking about the interesting environments that we should use this in, and part of it is to think about the methods themselves. And for example, are gradients enough? Should we do something else, like more of a generate and test approach, right, where we think about useful sub goals and then we test them out and we have some way of curating a collection of sub goals for the agent? I think that's all in substance quite open as a research direction.
Interesting. One question that's coming up for me is trying to think about the relationship between hierarchical RL, as you've described it, and curriculum learning. I guess one, just kind of riffing on, compare contrast, like curriculum learning is sequential in nature, whereas hierarchical RL, it could be more tree-like in the sense that you've got this, or maybe even like an ensemble, like the agent has this portfolio of strategies that it can employ. Um, Curriculum is maybe more training time, and hierarchical is more uh, inference time. I don't know if is that correct?
There is interesting relationships between curriculum and hierarchical RL. So on one hand, you could actually use curriculum learning in order to build a hierarchy. So if an agent, for example, goes through a curriculum, that curriculum could be targeted towards the agent learning options, right? So maybe yeah. So, and that would be very helpful because it would ensure that the agent has a set of options. And so when you go to the next stage of the curriculum, it's as if you've changed your action space in some sense, right? You don't have, if you've learned how to do multiplication, you don't have to learn that again. Now you have it as an option, and you can just employ it whenever it seems to be useful. And so curriculum learning can definitely be a path towards obtaining a hierarchical representation. But in hierarchical RL, you can do this also in different ways. So, for example, in a lot of the tasks that people have tried, they learn the options and they learn how to choose the options at the same time, end to end. So, an agent that, let's say, plays an Atari game is learning options for this game and using them in order to generate behavior, in order to explore, in order to represent its value function. Um, Now, of course, it's harder when you learn many things end to end at the same time. And so I think, that slows the agent down a little bit sometimes.
What does harder mean here? I mean, there's a whole, as you well know, field around multitask learning that suggests that it can be more computationally efficient to learn, or produce better results to learn multiple things at once.
Yeah, so this is the multitask learning, the multitask setup, and generally speaking, non-stationary setups, I think, is where hierarchical RL can be the most helpful. Because in such setups, it's worth investing some amount of time, slow learning at the beginning, so that afterwards you can do many more things, right? So, in a multitask setup, you might, for example, learn efficient exploration strategies. And those will help you because the tasks that come later, you'll still have to solve them. And now you know how to walk about your environment. Or, you might need to learn to use tools. You spend some time doing that, but then if you know how to use the tools, then you can go and be much more efficient in later tasks. So I think it depends on how wide the task distribution is and how long the agent is going to live in this environment, because in some sense we would expect that the benefit of hierarchical RL manifests more when the environment is more complicated and when the agent is going to have to live longer in this kind of complicated environment and be able to handle it.
Is there an analogy between hierarchical RL and, thinking about the different layers in a CNN, where the low levels are learning kind of more abstract things, shapes, textures, whatever, the higher layers are learning more complex shapes.
Yes,
How far would you want to take that analogy?
so the CNN is hierarchical in feature space, right? It's looking at different
Mhm.
resolutions in the feature
In the feature
space.
space, yeah.
Hierarchical RL is similar in spirit, but at the level of actions. So
Yeah.
lower layers would look at very fine resolution in terms of the actions being taken very quickly and lasting only little bits of time. Higher layers may look at actions that take a very long time to complete. It's not as sort of clean as a CNN in the sense
Right.
that these time scales can be variable, and we don't necessarily want to separate them out in very determined layers.
Right. And there's looping and it's not as clean at all.
Yeah, exactly. So, if you're thinking about cooking dinner, some things take a long time. Like maybe if you're baking bread, you have to knead the bread for a long time. And some things are very fast. And sometimes you just have to react. Like if the cat's on the table, you just have to do something immediately, right? And so the separation is not as fixed as you would have in the layers of a CNN. But it's the same kind of principle at the time scale. We want to have fine time scales and longer time scales at which we make decisions and at which we also make predictions about those decisions.
And is it useful at all to compare it to like an ensembling type of approach where you've got a portfolio of submodels that you can choose from at any given time?
Yeah, so you definitely have a portfolio of submodels and you can choose between them. It's not like ensembling in the sense that usually, so you have your portfolio, you make a choice. Once you made that choice, let's say to use a particular kind of model, you just go ahead and use it rather than looking at, let's say, the entire collection. I think there are interesting things to explore in terms of planning that would be even more like ensemble methods than the kinds of methods that we have now. And so, for example, right now, when we think about planning with temporally extended models, we think about big jumps over the time scale, but a model still usually predicts pretty much everything that will happen at the end of an option. So, at the same time, we might, if you have two hands, you might have, one hand doing one option and the other hand doing some other option, and you might want to make sort of separate predictions and then combine them. So I think there's a lot of room actually to think about what kind of composition operators we need. Right now, when we use temporally extended models, we use the same kinds of composition operators as in normal Markov decision processes. So we think about sequences and we think about stochastic choice. But there may be other interesting things to do, like thinking about concurrent execution, for example, and the outcomes of that.
Got it. Got it. Another area that you are exploring is continual reinforcement learning. Can you talk a little bit about that?
Yeah, definitely. So, continual reinforcement learning is really the natural way to do learning, right? It's really thinking about an agent that is in an environment that is much, much larger than the agent. It's enormous. And the agent has a lifetime and has to continue to learn and adapt throughout its lifetime. So, in reinforcement learning, often when we teach, for example, reinforcement learning classes, we talk about a Markov decision process that has a finite state space, it has a finite action space, and the agent is aiming to go back to certain states, understand which of these states are better, and so on. But in a continual learning setting, there may not be a Markov decision process. And if there is, maybe the agent's lifetime is much shorter than the entire environment, right? So the agent can't even hope to go to each state once in its lifetime. And the side effect of that is that there is pressure on the agent to use the data that it's seeing and to learn as much as possible from this data and just to continue learning over time. So this is the case where, for example, hierarchical reinforcement learning should be very helpful because the agent can learn certain abstractions, right? Making coffee, right? Going for a walk and so on. That would be helpful regardless of the situations that the agent is going to find itself in later. And it's also worth investing the computational effort in order to learn these kinds of representations. So I sometimes think about what would it look like to rewrite reinforcement learning without Markovian assumptions, right? Just imagine you have an agent, it's receiving observations, it's emitting actions. There is a reward signal because we want the agent to have a task, right? So there needs to be some goal specification. That's the reward. But otherwise, we don't make assumptions about Markovianness, about stationarity, right? About there being a stationary distribution of states that the agent is visiting. And one can still have algorithms that work under these settings. Um, there are some really simple things that we can think about. So, for example, doing usual temporal difference learning, but with fixed learning rates, right? Fixed learning rates mean that the agent is always paying more attention to the recent data, and that's a very easy way to think about handling the continual learning setup. It's probably not sufficient, right? Because it only sort of encourages the agent to pay attention to the recent data, but doesn't necessarily mean that the agent is trying to build these more abstract, useful representations. Um, so I think there's going to be a lot of interesting work in this area. We have actually a survey on archive that was co-led by my PhD student Kimia Ketrapal on continual reinforcement learning, never-ending reinforcement learning, and I'm quite excited to explore this further and to think about problem definitions, the mathematical limitations, and good algorithms, obviously, to handle these problems.
Do we have a sense for computationally, or in terms of sample complexity, like how you expect continual RL to play out relative to classical RL?
So that's a really great question. And it's an area where there's a lot of excitement and a lot of work on the theory side. So the first question to ask maybe is how do we talk about sample complexity in this case? And in theoretical RL, regret has been the measure of that people have thought of traditionally as a way to characterize sample complexity. So regret is the difference between the value of what you're currently doing compared to the optimal value, like how well could you do possibly in an environment. But if you're in a continual learning environment, how well could you possibly do is up for interpretation, right? So maybe the environment is not an MDP. There's not a unique optimal policy. What do you compare yourself against? And there's been some really interesting work by Ben Van Roy's research group at Stanford recently looking at that question and defining essentially classes of policies and thinking of regret within those classes of policies in this kind of continual learning setting. I think that this is something that we're going to have to think through. Like, what's the right measure of complexity? There's also tracking. This is a different approach that people have thought of. Tracking basically says if something changes in the environment, how quickly can you adapt to that change? And I think that's it's a little bit of a different perspective. Rich Sutton and some of his group at University of Alberta have looked at that in the past.
What's the idea with tracking?
As your environment is changing, you want to quickly adapt to those changes. So, for example, if you, let's say you had a grid world and you used to go on the left path always, but now that path is blocked, you go and you discover that it's blocked. How quickly can you find an alternative policy? And in some cases, agents can do this very quickly, right? Some of the agents can do this quickly. It all depends how good your exploration strategy is. But an alternative to that is to say the reward signal is changing. It's changing smoothly over time. Can you smoothly adapt your policy to track what would be the right actions right now? So there's these different kinds of changes, abrupt changes and more gradual changes, and you want to adapt. And of course, biological systems do this pretty well. And in our algorithms, if we use, in principle, if we use fixed learning rates, things like value functions would also adapt continually. But exploration policies, I think, may need to be rethought in this context. And specifically, a lot of exploration has been
And in
very
this
much rooted
context, continual or tracking in particular?
uh, continual, generally speaking,
Okay.
and
Yeah.
tracking as a special case.
Hmm.
Just because a lot of the work in RL exploration has been aimed at optimism in the face of uncertainty, right? So
Right.
if you don't know something, you should just be optimistic and go for it, which
Right.
is great if you're assuming that eventually you can go everywhere. But
Hmm.
if you have an environment that's very large and you can't go everywhere, you might need to do smarter things. So maybe information theoretic methods are more interesting in the setup, right? Or explicitly keeping track of uncertainty, or learning exploration strategies that are effective in the particular environment that the agent's at.
Hmm.
So there's a lot of avenues for future research in that setting.
Does the continual RL setting lend itself more directly to a time series type of problem, where you've got some agent that's making decisions that are presented to it over time, relative to exploring environments in any way?
So I think there are interesting continual learning problems in time series prediction outside of decision making too, for sure. Stock market prediction, to be very concrete, is one such example, right? But joking aside, there is. I think that the time series prediction setting is really interesting to think about because it avoids the problem of exploration, but it still allows us to think about how fast an agent might adapt and to think about how do we characterize the difficulty of these problems. So it's pretty clear intuitively that in some cases an agent may not be able to do anything. So if you had a time series where at every single time step there's some random bit that happens, and the distribution that you had on the current time step has nothing to do with the distribution on the next time step, well, there's nothing the agent can do, right? So this hints at the existence of impossibility results. But of course, in the real world, there's structure, right? So I think the setup allows us to think about what kinds of structure would allow an agent to learn successfully even if the environment is changing. So of course, for example, if there is gradual change in the environment, let's say your bit is drawn from a probability distribution whose mean is gradually shifting over time, then the agent can hope to learn how this shift is happening, right? And then perhaps even learn to anticipate what will happen next. Um, but smoothness is only one particular kind of structure. There may be others that are more interesting from a practical point of view.
To wrap things up, I'd love to have you comment broadly on the field of RL. Over the years, RL has it's been hard for folks to do, hard for folks to get up and running. How do you see that part of it evolving? What do you think are some of the big challenges going forward beyond the many that we've already talked about, of course?
Yeah, thank you for asking about that. I think RL has made tremendous progress, and it's again, from my point of view, it's the closest to biological learning, right? It's the closest paradigm that we have in the field of machine learning to biological learning. So it's very important for us to think about it. And DeepRL has, in fact, delivered many very surprising successes. Ranging from AlphaGo years back to more recently things like work by Marc-Gendron Belmar on routing loon balloons in the stratosphere using deep RL methods. Recent work by my colleague Martin Reed-Miller at DeepMind on plasma control for fusion reactors. These are very complicated control problems, and reinforcement learning algorithms can handle them and do a really great job. So that makes me feel very optimistic that we are able to scale RL and to really deliver some interesting practical results. At the same time, I think yes, there are challenges, and a lot of them have to do with these problems that we talked about, discovery and efficiency. how does an RL agent use its data very efficiently? How does it do efficient exploration? And how does it construct really good representations? And historically, reinforcement learning has relied a lot on other machine learning technology, for example, in order to build representation. So we use deep nets. Deep nets are wonderful, and they've led to a lot of these great successes. But in some sense, that specific set of methods was developed for supervised learning, right? And supervised learning is based on a different set of assumptions than RL, much more IID. And so the way that we've made progress historically has been to kind of take RL methods and make them more supervised learning like. Using replay buffers is a classical example of this in order to train, let's say, Q-learning with deep networks. I think it would be very useful for us to think about function approximation and optimization in the context of RL. And how do we do that efficiently? One of my students, Emmanuel Bengio, who just graduated, in fact, looked at this problem last year. And he discovered that looking at, let's say, atom optimizers in the context of RL doesn't give you that great results, right? In some cases, really does not combine well with temporal difference learning and similar algorithms. So I think one of the challenges for us is really to think about the function approximation and optimization problem in the context of RL, and also to think about this continual learning setup, because that's where we really want to go. If we're going to build general intelligent agents, they have to learn all the time. They have to learn in these settings where, Markovian structure doesn't hold. And so that's the frontier.
Awesome. Well, Doina, thanks so much for spending some time chatting with us and sharing a bit about what you've been up to in the space. Very cool stuff. You mentioned a bunch of research, your own and others, and we will try to collect that from you and be sure to include it on the show notes page. But once again, it's great chatting with you. Thank you for joining us.
Likewise. Thank you for having me.